Hello and welcome. Today we're diving deep into a critical aspect of modern distributed systems, low-latency Kafka consumer optimization. In the world of real-time applications, every millisecond counts, and understanding how to squeeze maximum performance from your message queues is a game changer. This lesson is designed for developers, architects, and anyone building highly responsive, event-driven systems. We'll move beyond the defaults and uncover the nuances that make a real difference in production. By the end of this session, you'll have a practical understanding of how to build systems that react faster than a blink. Specifically, you will be able to optimize Kafka consumers for ultra-fast message processing. You'll grasp the key settings that dictate how quickly your applications can react to new events. We'll also cover how to configure poll timeouts and fetch settings to achieve minimal latency, which are often overlooked but crucial details. You'll understand the architecture behind Stream Social's real-time notification delivery pipeline, giving you a concrete example to apply these concepts. And finally, you'll learn how to approach creating a monitoring dashboard to track every millisecond of your consumer's performance, ensuring you can maintain those ultra-low latencies. Let's get started. Think about your favorite social media app. When someone likes your post, you get a notification almost instantly, right? That's not magic. It's a meticulously optimized system processing millions of events per hour, often keeping latency under 100 milliseconds. This instant feedback loop is what users expect, and it's a critical performance metric for many modern applications. Our case study, Stream Social, faces the exact same challenge. Their users demand immediate notifications for messages, likes, and trending content. The problem is, default Kafka settings are typically geared towards throughput. That means handling a vast quantity of messages, rather than optimizing for latency, which is how quickly each individual message is processed. While throughput is vital for large-scale systems, for real-time notifications, speed is paramount. We need to flip that equation. For critical messages like direct messages or live alerts, Stream Social needs processing within 50 milliseconds. For important events such as likes or comments, under 100 milliseconds is the target. Even standard notifications like recommendations still need to be delivered within 500 milliseconds. This highlights why understanding the subtle differences between throughput and latency and how to prioritize one over the other is so crucial. To achieve these ultra-low latencies, we focus on three primary performance levers. First, the poll timeout. The poll duration method in Kafka tells your consumer how long to wait for new messages. Think of it like constantly checking your phone. A short timeout, say 1 to 10 milliseconds, means you're checking almost continuously. You'll see new messages immediately, but it's resource intensive, like constantly checking your battery. A long timeout, perhaps 500 milliseconds or more, means you check occasionally. Messages might pile up, but you save on CPU cycles. For our notification system where instant response is key, we'll aim for extremely short 1 millisecond timeouts. Next, we have fetch size. These settings control how Kafka batches messages before sending them to your consumer. Fetch.minBytes specifies the minimum data Kafka should return, and fetch.max.waitms is the maximum time Kafka waits to gather that minimum data. For low latency, we set fetch.minBytes to 1 byte, meaning don't wait for a batch, just send the message as soon as it's available, and fetch.max.waitms to a tiny 10 milliseconds, ensuring minimal delay if a batch isn't immediately full. Smaller fetches mean lower latency but more frequent network calls. For notifications, speed trumps network overhead. Finally, the processing loop itself. This is the engine that determines how fast you handle each message once it's received. While a single-threaded loop is simple, for high-performance needs, you might consider multi-threaded or, ideally, asynchronous processing. Asynchronous processing prevents slow downstream operations like making an API call to send a push notification from blocking other messages in your consumer loop. This allows your consumer to continue fetching and processing new messages while previous ones are still being delivered. Mastering these three levers is fundamental to achieving high-speed message delivery. Let's put these concepts in the context of Stream Social's architecture. Stream Social's notification system is a high-volume beast, handling over 50 million events per hour. These events originate from various sources: mobile apps sending user interactions, web clients triggering notifications, and back-end services generating alerts. To manage this scale and varying criticality, these events are fed into dedicated Kafka topics. For instance, user interactions handles likes and comments, system notifications covers trending topics, and real-time alerts is for urgent messages and live streams. Our consumer, the focus of today's lesson, reads from these notification topics. But here's where the consumer group strategy comes in. We don't just have one consumer. Instead, Stream Social employs 3 separate consumer groups, each meticulously optimized for different latency requirements. We have a critical notification consumer for DMs and live alerts, which is our 50 millisecond target. Then an important notification consumer for likes and comments, aiming for under 100 milliseconds. And finally, a standard notification consumer for recommendations with a more relaxed 500 millisecond target. This strategy allows independent scaling and optimization. The critical consumer group, for example, can use aggressive poll timeouts and fetch settings and be provisioned with more resources without impacting the processing of less urgent notifications. This separation is key to consistently meeting diverse SLAs for notification delivery. Now, let's trace a message's journey through this optimized system and understand the critical state transitions. It all begins when a producer sends an event, like a mobile app posting, "User A liked your post." This message then swiftly lands in a Kafka topic, specifically the critical notifications topic in our example. Our low-latency consumer pulls for this message, grabbing it in just 1 millisecond thanks to our optimized settings. Immediately after, the message enters the processing phase, where it's routed to the appropriate handler, taking perhaps 5 to 25 milliseconds. Then comes delivery, where a push notification is sent, typically involving a quick 2 millisecond network call. Finally, an offset commit confirms the successful processing, ensuring message durability. Throughout this journey, messages transition through various states. Initially, a message is pending, waiting in Kafka. Once the consumer picks it up, it moves to processing. After successful delivery, it becomes delivered. But what about errors? Robust systems account for these. If something goes wrong, the message enters a failed state. Based on retry policies, it might transition to retry, attempting delivery again with backoff. If all retries fail, it eventually moves to a dead letter state, indicating it couldn't be processed after maximum attempts. This structured flow and clear state management are vital for both performance and reliability in a high-volume notification system. To review, we've explored how dedicated consumer groups, optimized poll and fetch settings, and a clear understanding of message states contribute to building ultra-low latency Kafka consumers. Now, for your self-assessment, think about a scenario where a critical message processing step suddenly becomes slow. How would you diagnose whether it's a poll timeout, fetch size, or processing loop issue, and what would be your initial steps to mitigate it?